obviously, we're talking about efficiency today, and quite frankly, the reason that we chose this topic is because there's a tremendous amount of confusion out there on this subject. You would think there wouldn't be, but there actually is. And the confusion is about the terms and what they really mean. For instance, we hear the term combustion efficiency being used when in fact the individual is referring to thermal efficiency. Or we hear boiler or fuel to steam efficiency when in fact one is referring to thermal energy or thermal efficiency transfer. And this just goes on and on. So this session today is to establish some clarity about these terms, what they really mean, how they're arrived at, and what will negatively impact high efficiency performance. Now we'll also talk about ways of determining boiler efficiency along with some ways to improve it, thereby supplying the most cost-effective system for delivering steam or hot water to the process or to the space for heating, comfort heating. Just remember one thing as I go through this presentation today, that when we burn fuel in a boiler, we're burning cash. Cash which, if it's needlessly wasted, will cost the business a lot of money on its bottom line. So keep that in the background. When we talk about boiler efficiency, we can really boil it down to these basic terms. We have combustion efficiency, we have thermal efficiency, we also have fuel to steam or fuel to water efficiency if it's a hot water boiler. And that's also the same as boiler efficiency. So we could say that boiler efficiency and fuel to steam or fuel to water efficiency are synonymous terms. And then the last one we have, which has come out recently, which is a good way to evaluate boiler efficiency, is termed in-service efficiency. So today we'll be going through those and determine what they really mean. If we start with combustion efficiency, actually combustion is a chemical process. As you can see, it starts with a fuel which is primarily carbon-based. It could be natural gas, it could be oil, which has hydrogen in it. We also have, within that fuel, we've got possibly some sulfur if we're burning oil. We have nitrogen. Then we combine that with the air that we breathe, right, for combustion, which contains oxygen and nitrogen. And nitrogen, by the way, is about 78% of the air that we breathe that we use for combustion. And quite frankly, that goes along for the ride. It does nothing as far as oxidation is concerned. So then we have a burner that takes these elements, the chemistry goes on, oxidation occurs, and when that oxidation occurs, what we get is heat that comes out, the BTUs. We have some CO2, carbon dioxide, which some will refer to as the global warming gas. We have some water, and we have carbon monoxide, possibly. We try to keep that to a minimum, and we'll talk about that later. We might also have some nitrogen oxides and some sulfur oxides, depending upon the fuel. These are emissions that come out of this oxidation process that we have to contend with. So the burner itself is a combustor. It takes these elements, and it's the one that actually is the catalyst that gets this chemistry going. And for it to occur, we have to have time, temperature, and turbulence. That's what's going on within that burner. The temperature, of course, is supplied by a spark that ignites a pilot, which then ignites a main flame, which then, through spontaneous combustion, the oxidation continuously occurs. That burner also provides turbulence so that we can mix this fuel and this air together to give us good oxidation. But the question is, what gives us the time for combustion? We need the three: time, temperature, turbulence. What gives us the time? Well, that's the furnace. What you're looking at right here is a fire tube boiler, and I'm looking at it from the rear. The rear door is open, and you can see the gentleman here in the front that's inspecting the refractory around the burner throat. So this particular furnace needs to be properly designed and mated with the burner to give us proper oxidation and full combustion, efficient combustion. I have to be concerned about the flame shape so I don't impinge on these walls. and cause a cooling of the flame, a rapid cooling of the flame that could generate carbon monoxide, CO. I have to make sure it's properly matched. And what I'm trying to do here is take advantage of this radiant heating surface. Now, if we look at radiant heat transfer, we're talking about things like emissivity. We're talking about the theory of Stefan Boltzmann, who takes a look at radiant energy and how effective it can be if properly employed. Remember, we've got a huge delta T here. You've got temperatures in this furnace which are over 2,000 degrees. We've got a water side temperature on the other side that might be in the 300 degree range or less. Tremendous delta T. And as a result, the heat transfer is very, very extreme, and we want to take advantage of that. And that's one of the things that boiler designers today are doing, is trying to take more and more control and more advantage of radiant heat transfer in the furnace. But all in all, when everything is said and done, that furnace, its geometry, its length, its diameter, its configuration, its volume will determine the time. So, for us to be able to achieve 100% combustion efficiency, I have to burn every single molecule of fuel. I will have no excess air. I'll have no hydrocarbon. I'll have no CO. That is called perfect combustion. If you want to put a number on it, it's 100%. It's stoichiometric combustion. But you know that's not found in the field. We don't do that in the field. We don't set it up in the field that way because it could be dangerous. If we start to go fuel rich, we don't have proper control, we can have what we call a fireside occurrence in this business. And the reason for that is variances in the atmosphere that we have positively no control over. The ambient temperature of the room, which is our combustion air. The barometric pressure, which can rise or fall. The relative humidity, the calorific value of the fuel. All these variables make us set these burners up at something less than stoichiometric. We've got to go air on the conservative, so we will add additional excess air to keep us safe. So what is excess air? Well, it's nothing more than that percentage of air which is above the stoichiometric, 100% combustion efficiency. Remember, when we talk about combustion efficiency, we are only talking about the effectiveness of that burner to properly oxidize the fuel, the air, and combust. So when we talk about excess air, it's that percent of air, that volume of air, which is over stoichiometric combustion. Let me show you a curve. If we look right here where this red arrow is and my little red dot, right here is 100% combustion efficiency, stoichiometric combustion. I've got no excess air on here. I've got no CO. I'm burning everything. That's stoichiometric combustion. But the way we set these burners up is to go air on the right side of the curve in order to give us that margin of air. So we don't go fuel rich and have a post-combustion explosion in our furnace. So you can see here as I go to the right of the curve, here's 100%. As I go approaching 20% excess air, of course, my oxygen is increasing. This line here is showing me my carbon dioxide, the CO2 level. As I combust any carbon-based fuel, I'm going to give off carbon dioxide, CO2. If a tree falls in a forest and it decays, as it decays, it gives off CO2. Anytime we're involved with carbon and it disintegrates, we generate carbon dioxide. Now, here I'm burning natural gas. The CO2 value at stoichiometric is going to be in about the 11% range. That's as high as I can go. If I was burning number 2 oil, it'd be up around the 14% range. But I'm burning natural gas here. So this is my CO2 level. Now, as I go to the left of the curve and I start to go fuel rich, you can see what's happening to my CO right here. It's beginning to increase. Got to be very careful about that. Let me show you another curve. Here you see, now this is just the inverse of what I showed you before, but follow me now. This is zero right here would be essentially 15% excess air or 3% O2. They're synonymous. We can talk about these terms interchangeably. 3% O2 is the same as 15% excess air. This is where we would like to have our boilers most of the time. If they can hold 3% O2, 15% excess air, that would be just great. But what does that really mean? Well, if I take a look over here, where I would be at 100% combustion efficiency, I've essentially added 15% excess air or 15% more mass to the overall oxidation, to the overall mass of gas within that boiler itself. Okay, that's what I'm doing with this excess air, 15% more. Now, what we see a lot of in the field today are boilers operating in this range, 7% O2, 45% excess air. Not at all uncommon. And so what that has essentially done, when I go from 3% excess air to 7% excess air, I've increased it 4%, and when you go through the math and the computations, I've lost 2% in my overall efficiency. So I'm trying to hold here, but what I'm finding out there is a lot of this. Needless waste of energy, and it gets involved with combustion. Now, if you want to call that combustion efficiency, I suppose you could. But that's what's really going on. So what we're saying here, when we talk about combustion, we're not talking about 100% combustion or 95% combustion efficiency. If you can hold 3% O2 most of the time when you're firing and handling load, we call this very effective combustion, good combustion. Now, if I might show you another curve here. Here you see a firing rate of 10% to 100%. With most boilers today that are out there, there are some differences now. There are some differences to this. But most boilers, when they're operating in this particular range, which is in the 60 to 70% range, this is where you're going to find a lot of them. And you can see at this particular point, I'm at about, what, 4.5% O2. That's about 25% excess air. This is where you're going to find a lot of boilers. There's also boilers out there today that'll be able to hold pretty close to that 3%, even in this operating range. Now, this operating range of 60 to 70% gets very, very important as we talk about something else a little bit later. So keep that in mind. But the main thing to realize here is that as you decrease in firing rate, the amount of excess air will increase. More in some units, less in others. But it's certainly something that you engineers ought to keep in mind, especially as it relates to how you size boilers for load. You don't want a boiler hanging in this area all the time. I mentioned before that there's variables that we have no control over. One of the biggest threats that we have to good, safe, and good efficient combustion is the temperature in the room, the ambient air, the secondary air that we use for combustion. Here what we did is we set this boiler up. It was 80 degrees in the boiler room. The barometric pressure was 29 inches of mercury, and we set it up at 15% excess air, which is 3% O2. Not at all uncommon, especially down south in the summertime. That temperature in the boiler room creeps to 100. You've got no control over that. Or it goes to 120. Look what happens to my margin of error. 9.6, 1.1. I'm getting close to stoichiometric here. Pretty dangerous. Now, if I go the other way, I'm blowing that nitrogen out the window, right? 78% of our air, where I go from 80 degrees to 60 degrees in that boiler room here in Milwaukee. The air is now denser, it's colder, it's denser, and as a result, my excess air increases. I'm just heating that air and blowing it out the stack. So what do I do about that? This is where an O2 trim system can really help. If you have a boiler room that varies in temperature and you've got no control over it, and or you've got a boiler that modulates a lot, especially one with single point positioning, a lot of linkage, it's a good candidate for O2 trim. If that boiler room doesn't vary in temperature, if it doesn't modulate a lot, it could be a waste of money. Now, the other thing that's very important to keep in mind when we're talking about combustion is supplying the proper amount of air for that combustion process. And a good rule of thumb that we've used over the years is 10 CFM per boiler horsepower. 8 CFM of that, of course, is to support the combustion process, to oxidize the fuel, and 2 CFM is used for ventilation. Now, that's not to keep the boiler operator comfortable. It's really to make sure that that room does not go negative. Then you take that, let's say we've got a 300 horsepower boiler, we need 3,000 CFM of air. You divide that by 250, and that will give you the cross-sectional area in the room that we need for ventilation. Okay, let's move on to the next efficiency criteria that we would like to define, and that's thermal efficiency. Now, what thermal efficiency is, it's nothing more than the ability of this heat exchanger that you see right here. Here's my burner. It's firing into the furnace. That's the radiant area right there, as you can see, in the furnace. And then I've got these convective passes. This fire tube boiler has these tubes. The hot gases are going through it. When I talk about thermal efficiency, I'm only talking about the ability of this heat exchanger to absorb the heat, to take that heat, put it into the water, and generate hot water or steam. That's all I'm talking about. There are also, and of course that energy is going to vary as I turn the burner down. And I can have a 4-to-1 turn down, I could have a 10-to-1 turn down, I could have a 20-to-1 turn down burner. It's all about the amount of energy going into that unit that is being absorbed by that heat exchanger, so it goes into the water to make hot water or steam. It does not consider radiation and convection losses, okay? So that means that those radiation and convection losses are lost somewhere. They're not going into the water to make steam or hot water. Keep that in mind. We'll address it a little bit later. Now, one of the things that boiler manufacturers and designers are doing today to improve the overall convective heat transfer in the boiler, to enhance that thermal heat transfer, increase the overall thermal efficiency, is to add extended surfaces inside of those tubes to break up the gas, to get away from the laminar flow, which increases the Reynolds numbers, which is nothing more than a ratio between inertial and viscous forces, to increase the Reynolds numbers, and also the heat transfer coefficient, which is the heat flux ratio against delta T. So that's all the technical jargon that goes on, but essentially all I'm trying to do is break that gas up so I've got good contact with all surfaces on the heat transfer side of that tube to get it into the water. And as a result, what I can do is reduce the heat transfer surface by as much as 85%. And why do I want to do that? Well, I can put more energy into the furnace, number one, reduce the convection section, and reduce the overall size of this, let's say, fire tube, horizontal fire tube boiler. That's why the industry is beginning to gravitate in that direction. So that's thermal efficiency. Now, what about fuel to steam or fuel to water efficiency? Here, what you have is the net amount of BTUs that will be going to the process or going to heat the building, okay, the hot water to heat the building hydronically. It's net of radiation and convection losses. Now, if we look at various boilers, those convection losses can differ anywhere from 0.5% to 2%. In other words, in a large fire tube boiler like this, It could be 2%, 1.5%. On a small little vertical fire tube like this, might only be 0.5 or 0.75%. It depends upon the mass. Now remember, when we measure radiation and convection losses, and the reason I mentioned turn down before when I talked about thermal efficiency, is it's all based on input, all right? So, the fact of the matter is, when we're considering radiation and convection losses, they get larger as the input decreases. Well, why would that be? Well, the reason is that your mass within the boiler itself, let's say that we're operating at 100 pounds. The saturation equivalent to that is 338 degrees. Well, regardless of where I turn this burner down, regardless of where I turn it, that temperature is not going to change. So as I decrease the firing rate, therefore the input, I'm dividing into an ever smaller number. So therefore the radiation and convection losses climb inversely to input. All right? Well, how are boilers rated? That's the next question. Keep this in mind. When we, as boiler manufacturers and promoters, are selling boilers, what the engineer starts with is a catalog or engineering data. And we're going to catalog that boiler saying it's a 100 horsepower boiler. Well, that's based at full fire, at 0 gauge pressure, okay? All I've got is 14.7 pounds at sea level, so my gauge is reading 0. My feed water, keep this in mind, is 212 degrees. Now, how many boilers out there are fed with 212 degree water? But that's how we base the sizing of these boilers initially. And then the engineer has to be smart enough to be able to make accommodations accordingly based on the load or what he's heating or what the process might be or so on, and size the boiler accordingly. If the feed water temperature or the pressure, the operating pressure, is going to be more than that, and obviously it will be. So what else do I have to be aware of? Well, when we're looking at boiler efficiency and how well we're doing, you've got to remember that you have to benchmark the information that you're looking for. So let's say that we're looking at the stack temperature coming out of that boiler. The stack temperature in an efficient boiler is going to run anywhere between 50 and 100 degrees above the saturation pressure or temperature based on pressure. So when we're looking at efficiency and we want to evaluate it, the first criteria we have to look at is what's the operating pressure? Because that's got an equivalent temperature. More importantly than that even is what's the firing rate? Am I at low fire, medium fire, high fire when this stack temperature is occurring? What's the ambient temperature in the room? Is it 100 degrees? Is it 60 degrees? Because that's going to add to the gross temperature of that stack. And then lastly, what's the feed water temperature? What's coming into that boiler? Is it 212? No. 180? Could be. 227 coming out of a deaerator? Could be that. All right. What else do I have to be aware of? Once I've established that benchmark or those benchmarks, and I now have something logged in my boiler room log that says that my steam temperature is now 395 degrees. I'm operating at 100 pounds. The next day you come in and my firing rate is high fire. The ambient temperature in the room is 90 degrees. And my feed water temperature is 180. You come in the room the next day, or 2 hours later, the criteria is all the same, but my stack temperature has gone up. That costs you 1% in fuel to steam efficiency. And what causes that? Sooting on the fire side, scaling on the water side. I'm impeding the heat transfer across those tubes, whether it be a water tube or a fire tube. So the first thing is to make sure you've got a very reliable stack thermometer in that stack, and you very conscientiously log temperatures against pressure, firing rate, ambient temperature, and feed water temperature. Very, very, very important. Because when you see something like I'm showing you right now occur, something's gone on with that boiler. And 9 chances out of 10, it's the the water side of that boiler or the fire side that's either gotten fouled from soot or scale. Another example, follow me here. I'm at 220 degrees is my flue gas temperature. I've gone to 260, and you can see right here in the numbers, I've gone from 84% to 83%. I've lost 1% based on that 40 degrees. Now here's something else that's really interesting when I talk about the confusion in terms out there. This is really a fuel to steam or a thermal efficiency chart, but look what they call it, combustion efficiency for natural gas. It has nothing to do with combustion efficiency, really. We're looking at either fuel to steam or fuel to water or possibly a thermal efficiency. If the radiation convection losses are included, it's thermal. If they're netted, it's fuel to steam. So that's where how this confusion is promulgated. All right, I talked about feed water temperature. Let's just take a look at this particular chart to see what I mean. When we as boiler manufacturers catalog our boilers, it's from and at 212 degree feed water, 0 gauge pressure, and I get 34.5 pounds of steam per hour per boiler horsepower. When I drop that feed water temperature to 100 degrees, keep my operating pressure at 0 gauge, I go to 30.9. If I go to 100 pounds of operating pressure, and I'm at 212 degree feed water, I've lost a little bit, 34.5 to 33.2 because of the operating pressure increase, more BTUs required for sensible energy to get that temperature up so I can start to apply my latent energy. That's why that is. But anyway, look at this drop because of the 100 pound operating, 100 degree feed water. I'm down to 29.8. So when I thought I was going to get 34.5 because of these conditions, I'm down to less than 30 pounds per hour, per boiler horsepower. The importance, operating pressure, feed water. Now also, let's talk about the boiler's sweet spot. We've got a number of boilers that we manufacture, various types. They're configured with various controls and burners and so on and so forth. But every one of those is unique. Each one of those types has its own signature based on horsepower, fuel, burner, and so on. It's got its own signature. It's got its own sweet spot. And that becomes very, very important when we understand that particular boiler. We understand the load so that I can select the proper boiler to handle that particular load so it's operating in its sweet spot most of the time. Now, as I said before, we find a lot of boilers out there that are operating at about 60% of the firing rate. Now, in this particular case, with this boiler, and there's a lot of them out there, and we just took an overall average, this is the sweet spot. That's where you want it to run. You don't want it to be running down here or down here and then cycling a lot, and we'll talk about that as well. You want it to be operating at the sweet spot. So you got to find out from that manufacturer, from that sales engineer, if I put this boiler in, where is it most efficient? So I can size my load accordingly and keep it there as much as I possibly can. Well, then how do I measure efficiency? Well, there's really two methods to measuring efficiency. It's either the input-output or the heat loss method. Now, if we go to the input-output method, it's much more complicated. And quite frankly, in all the years that I've been in this business, and I think Rakesh will attest to this, who is on the expert panel here, the input-output method the juice may not be worth the squeeze. You have to go through an awful lot to conduct an input-output test. In other words, it involves calorimeters, which are devices to be able to determine the amount of moisture in the steam coming out of that nozzle. We also have to have flow meters. It might be a steam flow meter. It could be a water flow meter, because I want to make sure that what is going, I can calculate what's coming out of the boiler, and obviously if I know what's going in, I know what's coming out. Okay, so I can either map my feed water or I can map my steam output. And then, of course, I look at stack temperature, I look at the constituents of the gas, I look at my dry gas temperatures, I look at the the moisture losses and so on. That all goes into the input-output method. And even though it can be very, very precise, it requires a lot of labor, instrumentation, and a lot of complexity. We've found over the years that probably the best and most efficient way to go about this is just the heat loss method. And what this does is it takes into consideration what the stack temperature is above the saturated temperature of the boiler itself. It takes into consideration the constituents in that gas. And it also accounts for the moisture losses. So what we're looking for is the temperature, the carbon dioxide, the excess O2, what it is. Remember, I'm saying we're trying to hold as close to 3% O2 as we possibly can. It'll then give us a net efficiency overall. It'll also say whether or not we've got any carbon monoxide in that gas, if we've got any nitrogen oxides, which, of course, nitrogen oxide, NO and NO2 is a precursor to smog, so we want to limit that, especially in places like California and Texas and Louisiana and New Jersey and other places. That's what this stack gas analyzer that you see here will do for us. So it's relatively simple, but by golly, when you go through an input-output and you compare it to the stack gas analysis, we're often very, very close. So I would rather, lean toward expediency as opposed to something that would be more complex when I'm looking at how I determine my overall efficiency. Now, let's look at in-service efficiency. Well, the criteria for that: stack losses, radiation and convection losses. What are the startup losses? What do they mean? Cycling losses, which really result in purge losses. Turn-down losses, which is really, we're looking at excess air. And as I said before, most boilers, when they turn down, the excess air rises. What are the blowdown losses? And what are the changing load response? What's the changing load response? In other words, how effective is this boiler in reacting to load swing? So that's in-service efficiency criteria. So let's look at those. Well, we've already addressed the stack losses and the R&C losses, so we'll move right into the startup losses. Startup losses really assumes that a boiler is offline and it's cold, so it's at ambient temperature. Now here I've got a fire tube boiler, which has got a lot of mass, right? It's 5 square feet per boiler horsepower, against a vertical boiler right here that has far less mass, let's say. Maybe it's only 2 or 2.5 square feet per boiler horsepower. The whole point is that if I'm starting this boiler to meet load versus this boiler, and they're both at ambient, obviously this boiler is going to heat up faster, and it's going to catch that load faster. No doubt about it. And so the engineer might say, all right, I'm going to put in a bank of these as opposed to 1 or 2 of these. But don't forget one other thing about this. Once this boiler comes up to pressure, it has a lot of thermal mass. It's got possibly a lot of refractory, a lot of residual heat. So once it comes up to temperature, even when that burner cycles off, it continues to steam. And I don't think anybody would disagree that a boiler that's not firing is more efficient than anything. But this is really true. These larger mass boilers, once they come up to temperature, they hold that heat. So then once they start getting swings within the load itself, this thing will respond just about as quickly as this one. But it all depends upon that load. Should I go modular, low heating surface, low mass? Should I go larger boiler? Less number, but maybe it's got turned down to match the duplicity that would be required for more modular type units. What about cycling losses? I'll tell you, this is one of the worst culprits as far as energy loss is concerned, cycling. Where boilers have been put in maybe years ago, they still have a lot of useful life, but they don't have proper turn down, they haven't matched that load. We've done a lot of things to the process, we've done a lot of things to the building, it's much more efficient, and these babies are cycling, turning on and off 15, 20 times, or more than that, an hour. And as a result, we are blowing energy out the stack, we're blowing dollar bills out that stack because of all the cycling losses, cycling on and cycling off. This is where turn down becomes so important too. So maybe you've got an older boiler that's still in very, very good shape. You could retrofit it with a high turn down burner, or keep the same burner but do something with the overall linkage and the way it is controlled as far as the damper is controlled and how it's all configured, and add 10-to-1 to it if need be, if it's a 4-to-1 turn down. That can be done. Keep this boiler online. It seems like an oxymoron, but actually that boiler staying online is a lot more efficient than having it cycle on and off 15, 20 times an hour. Why is that? The pre- and post-purge losses. Every time that boiler goes down, it has to go through a post-purge loss. Post-purge. You're blowing ambient air through that boiler and chilling it down. Then it goes through a pre-purge before ignition. That's another 90 seconds or a minute and a half blowing air through that boiler. You don't want it to do that. You want to keep it online. Because all we're doing is blowing that energy out the stack into the atmosphere, heating the ducts. That's all we're doing. And remember, when we're talking about burning fuel, we're talking about burning dollars, cash. Now, blowdown losses was also a part of the criteria of in-service efficiency. If we've got continuous blowdown with a boiler, I'm trying to control the TDS level at 1,500 TDS of 1,500, or maybe it's a bit less, or maybe a bit higher. Our water chemical engineer has advocated a certain water treatment plan to control the total dissolved solids. That boiler is skimming water off the top, and it either goes through a separator and into the sewer, or it can go into a shell and tube heater and recover those BTUs, put it in the feed water before it goes to the deaerator or feed system. Why not reclaim those BTUs? But remember something. Don't ever try to recapture bottom blowdown. Bottom blow is there to be performed once or twice a day, depending upon the chemical analysis and the requirement. Goes into a separator and you waste it, because otherwise you'll foul this with sludge, and it's so intermittent. As I said, once or twice a day, the juice isn't worth the squeeze in paying for any recovery, really. So bottom blow, don't recover. Surface blow, think about it seriously. What about changing load response? Part of the in-service efficiency. Thinking that it requires more energy to get this big boiler to respond. Well, from a cold start, absolutely right. If you've got a small modular type unit or a commercial type water tube product that you see here, these babies respond very, very, very quickly. And maybe based on the characteristics of that load, that's what you need. But don't ever forget that these bigger boilers that you might already have and have invested a lot of money in, and you've added controls and burners and so on, can do real well too if they're properly controlled and programmed, so that once they come up to pressure, they can respond pretty good. Now, I will say that water tube boilers innately will respond much better than a fire tube will to what I would call swing loads, varying loads, because they don't have as much mass. They can respond very, very well. But that doesn't mean that you throw something like this out. It depends upon that load, what you have, and what might be done to it to make it respond better. So, let's recap a little bit. Combustion efficiency takeaway. Stoichiometric combustion is 100% combustion efficiency. To be safe, burners are set up with excess air about above stoichiometric to provide safety, normally 15% excess air. Clean combustion with consistent excess air throughout the firing range and 0 to a trace of CO, we're talking maybe no more than 50 parts, is considered excellent combustion. So that's the takeaway from combustion efficiency. Thermal efficiency, remember, it does not consider radiation and convection losses. So those BTUs are going into the room that's already 100 degrees. It's not going into the process, not going into the hot water to heat that building. All right? What you want to look at is fuel to steam efficiency or fuel to water efficiency. So those are your takeaways. In-service efficiency takeaways. Cycling losses can cost 15% or more in overall efficiency. Never capture the bottom blow, but think seriously about the blowdown heat recovery for continuous blowdown. Responding to load quickly is determined by the boiler mass and the water temperature within the vessel. Keep those all in mind. There's good arguments for modular type low heating surface boilers, but there's also good arguments for a larger mass boiler too. It depends upon the application. So, attaining the most efficient boiler system, well, first of all, and I think I've hammered this home, it starts with understanding this load, first of all. Understand the load so I can properly apply the proper boiler for that load, properly sized, with the proper turn down to match that load as it varies from low to high fire. Also need boiler burner compatibility. In most packages out there today, the engineers have done a good job trying to make these boilers and burners compatible so they deliver the highest radiant efficiency as well as convective heat transfer and radiant heat transfer to give us the highest fuel to steam efficiency. And of course, what also is very important is how do we control these boilers from a burner management standpoint and a combustion control standpoint. Let's get rid of the single point positioning. Let's go with parallel positioning. So I get rid of the hysteresis and the stretch and the slip in those single point positioning linkage arms and rods. Go with individual motorized actuators for the fuel, the air, and if you've got flue gas recirculation because you're trying to limit the nitrogen oxides, the NOx, individual actuators tied into a central control system. So the operator knows all the time what's going on, and we can better control our fuel-air relationship. And of course, size for the optimum firing rate. We want that boiler to hang at its optimum. Some boilers might be 60% firing rate, some might be 80, 90% firing rate. Your sales engineer, the boiler manufacturer should know what that is. And of course, combine that with turn down so that when we begin to slip off load, we can still keep that boiler on and firing. Also, take a look at ways that we can improve the overall efficiency of that boiler. Remember, a boiler can only do so much. You get 84, 85% fuel to steam efficiency out of a boiler. It's done about all it can do. So if I want to get that up to the above 85%, let's say, I've got to think about external things that I can employ. Blowdown heat recovery I mentioned. What about an economizer on the stack? It could be a condensing economizer. It could be a standard economizer. If I've got a lot of hot water need, where I can take 55-degree water and take it through the secondary exchanger and an economizer and bring that water to a tank for whatever potable use might be considered, I can save boatloads of bucks here. I can take that fuel to steam efficiency up to the 90% mark. So that's what I'm looking at, conserving that valuable resource of oil and gas, the finite resources that come back to us not just as far as the environment is concerned, but come back to us in terms of dollars in the pocket.